Electricity and electronics is the study and control of electron flow. Now, when you dissect atoms, electrons are the particles that spin around the outer perimeter of the atom. So you can see the root word electron in electricity and electronics. These electrons can jump from one atom to another. Now, in some materials, this happens very easily. In other materials, it's very difficult for an electron to jump from one atom to another. Materials in which electrons flow easily are called conductors. Materials which are very hard for electron flow are called insulators. Now, there is no such thing as a material that will not conduct electricity. If you apply enough electrical force, everything will conduct electricity. But for the moment, we will pretend that insulators do not conduct electricity at all. So, what are some examples of conductors? Copper is one that comes to mind. Aluminum would be another. Steel. So, basically most metals, in fact. Now, gold and silver are excellent conductors. In fact, spacecraft use a lot of gold for wiring because gold doesn't rust either. So it's very reliable. So what are some examples of insulators that you can think of? Glass, plastic, wood, cardboard, paper, most fabrics, ceramics, like plates and cups. So if you want to stop electricity from flowing, you'll use an insulator of some kind. If you want to allow electricity to get from one place to another, you will use a conductor. But now, what about water? Is it a conductor or an insulator? Now, you might be inclined to say that water is a conductor. In fact, water is actually a pretty good insulator. So why then is there all the fuss with warning about all these commercials, public safety messages about safety around water with electricity? Why'd they have that guy in the pool with the pool net, and he's going around scooping up leaves and accidentally pokes the aluminum handle through a light bulb and he gets electrocuted? If water is a lousy conductor, why all these warnings? Which are very real warnings, by the way. Well, the reason has to do with chemistry. What's in pool water? Chlorine or salt, depending on the pool. In either case, it is the addition of the chemical that makes the water a conductor. So, if we take perfectly pure water, distilled water, which is a very good insulator, if we add just a teensy bit of salt to the water, is that water a conductor or an insulator? It's no longer an insulator, but it's a really lousy conductor. So let's add just a little bit more salt to the water. It is now just a little bit more of a conductor, but is still a really lousy at conducting electricity. And now it's not a very good insulator either. So the more salt you add, the better the conductor it becomes, and the worse of an insulator it becomes. But it's in that middle state where it's neither a conductor nor an insulator, which is very useful to us. We call this a resistor. It resists the flow of electricity. Now, essentially, conductors have very low resistance. Insulators have a very high resistance. Now, electricity is measured in two different ways: voltage and current. Current, measured in amps, is the number of electrons that actually flow. Voltage is how much pressure is pushing those electrons to move. Resistance is how much the material is pushing back against the current flow. And resistance is measured in ohms. Voltage is indicated by the letter V. The current is indicated by the letter A or sometimes I. The resistance is indicated by a funny Greek letter called omega. For now, think of it all like a garden hose. The amount of water coming out is the current. The amount of pressure in the hose would be like the voltage. If you bend the hose and kink it, that is resisting the flow of current. Now, batteries are typically low voltage. Take, for instance, a AAA battery. It pushes the electrons with 1.5 volts. You can touch both ends of the battery and never feel a thing. Now, how much voltage do you think a AA battery might put out? You might think it's more voltage because the battery is bigger, but it's actually the same voltage, 1.5 volts. But an AA battery being larger than the AAA battery can source more current, more electrons, more amps. Well, what about a D cell battery? What voltage do you think it pushes out? Now, if you guessed 1.5 volts, you're actually right. But look at the size difference. D batteries can pump out a lot of current. Now, this is why flashlights typically use D cell batteries, because light bulbs take a lot of current. So these batteries are all quite low in voltage. These single cell batteries, because of their chemistry and physical makeup, will typically put out 1.5 volts. What voltage do you think these square batteries put out? That's a bit of an easy one because usually they're called 9-volt batteries. You can guess why. Now, they have a higher voltage, but still quite low. If you wet your skin and put the battery posts against your tongue or skin, you'll get the unpleasant feeling of electricity flowing across and through your skin. So higher voltage was able to overcome the resistance of your skin and able to cause your skin to conduct electricity. But it's fairly harmless. There has been discussion about whether or not putting a 9-volt battery against your tongue actually causes damage or not. So I'd recommend it against it. Recommend against it, not recommend it. But to make the 9 volts, what the manufacturer does is stack 6 miniature batteries on top of each other, each of which produces 1.5 volts, adding up to 9 volts. But look at the size of those mini batteries compared to even a AAA battery. These mini batteries are very small. Now, like the smaller batteries, these teeny cells can't put out a lot of current. So 9-volt batteries are typically reserved for jobs that don't need a lot of current. Lantern batteries like these put out 6 volts, but it's much the same as a 9-volt battery. They simply stacked smaller batteries to make a bigger one. These long batteries are like 2 C cells stuck end to end. Then they wire 2 of these packs together, end to end. The individual cells are only producing 1.5 volts, but they stack them so the voltage, total voltage, adds up to 6 volts. Let's move upscale to a car battery. Hey, look at the size of this thing compared to a 9-volt battery. So, what voltage do you think they put out? Surprisingly, it's still a very low voltage. Now, they are called 12-volt batteries, though in reality, the voltage usually hovers around 13.5 volts. We'll say it's 12 volts. Now, while it is a low voltage, it is high enough that your sweaty arm across the posts will produce that wonderfully uncomfortable feeling of electricity running through your skin. However, car batteries have very special dangers. In particular, look at the size of it. The amount of current it can put out is incredible. A car battery can put out hundreds of amps. You can arc weld metal and melt metal with a car battery, not because of the voltage, but the sheer volume of current it can pump out. This is also why the wires coming off the battery are so huge. They need to be big in order to handle the incredible current without actually melting. So if you're working on a car battery and you've got a wrench and you're loosening off the bolts on one post, if you accidentally cross over and touch one post to the other, several things will happen. 1, you'll get a lot of sparks. 2, the wrench can get really hot, really fast, and you can get burnt. 3, car batteries, when charging, also give off extremely explosive hydrogen gas, and they're filled with an incredibly potent acid. So the sparks caused by you short-circuiting the posts with your wrench generate sparks, which ignites the hydrogen gas, which causes the battery to explode, sending very potent sulfuric acid all over the place. In your eyes, on your skin and clothes, nearby bystanders, etc. So now, you're blinded and being eaten by acid and have a fire on your hands. All of that, and it's only 12 volts. The point I want to make here is that it's not just the voltage that's dangerous, but current as well. Now, batteries have a plus and a minus pole to them. Electrons flow out of the minus end of the battery and into the plus end of the battery. It's counterintuitive at first, but that's the direction the electrons move. The thing with cars is that the negative or minus pole of the battery is actually connected to the car body. So this is a further danger when working on car batteries. You can short circuit the battery with your wrench if you accidentally put the wrench between the plus side of the battery and any metal part of the car. So if you're going to remove a battery from a car, you remove the minus wire first. This way, if you accidentally touch the wrench between the post and the car body, it doesn't matter because you're only connecting the minus side of the battery with the minus side. You won't get any current flow. Also, once that wire is removed, you've now removed the connection from the battery to the car body as well, so you can safely work on removing the second wire without fear of accidentally short-circuiting to the car body. Now, we call that connection to the car body a ground connection. Now, we can make a connection to the negative post of the battery by simply connecting to any metal part of the car. Now, most battery cells, as you saw, typically produce 1.5 volts. This is just because of the chemistry of the battery. Rechargeable batteries like nickel-cadmium, because of the chemistry of the battery, typically produce about 1.25 volts in a cell. There is a fairly new battery type that's so efficient, lightweight, and reliable that it has stormed its way onto the consumer market. That is the lithium ion battery. Because of their chemistry and construction, typically they produce around 3 volts per cell. Now, almost all batteries contain nasty acids, so don't open them up. And if they leak, handle them with gloves and wash everything down so you don't get acid burns. We saw how the car battery had special dangers with fire and explosion. Lithium ion batteries also have a unique danger of them because of their composition. If a lithium ion battery even gets hit or punctured, it can burn with intense heat. The bigger the battery, the bigger the burn. This is why lithium ion batteries have very specific chargers, because even if you charge them wrong, they can catch fire and then set everything else on fire in seconds. So for the moment, my recommendation is to stay away from lithium ion batteries. Once we get a handle on how to use and control electricity, you'll then have an idea of what to do to use them safely.